Okay, well, welcome everyone to this meeting of the virtual IMS user group, and thank you for joining us. I'm Trevor Eddles, I'm CEO of iTechEd. We're a mainframe consultancy, analysis and technical authoring organisation. We're responsible for the content on the virtual IMS website, and we produce the newsletters. And we also look after the virtual CICS user group, if you're interested in that. Anyway, first of all then, let me run through the agenda for this meeting. As usual, most of the meeting will be taken up with a presentation, and today our guest presenter is Scott Quillisi. He's principal at SQ Data Corporation, and his talk is called IMS CDC to Kafka, Performance and Tuning. And a copy of the slides from this presentation will be on our website later today. And by the way, if you've missed any of our previous meetings, you can download copies of the presentations from the website. And of course, you can listen again to them. There's a link on the resources page. Excuse me. Following Scott's presentation and any questions you have for him, we'll move on to the latest IMS news, latest IMS related articles. Feedback request is there to remind me to ask you for your feedback about this virtual meeting, and then I'll give you the dates and times for the next couple of meetings. Yeah, so that's the plan. I'm anticipating that this whole meeting will last about 45 minutes-ish. Anyway, as I just said, today's presentation is from Scott Quillisi. Scott is a co-founder of SQ Data, a US-based independent software vendor that specializes in high-performance data replication and change data capture solutions for mainframes. That's IMS, vSAM, DB2, and he also works with distributed databases. He's got almost 40 years of experience, and Scott is considered by his peers to be an expert in database replication technology and deployment. Over the past few years, Scott has been working with larger mainframe customers on their real-time data streaming initiatives, most of which involve high-volume ingestion of operational data into fast targets such as Kafka and Hadoop using SQ Data's mainframe CDC connector technology. Okay, so Scott, I'd like to thank you very much for being with us today. And what I'm going to do now is pass control over to you. I'm just going to make you, oops, no, not that one, sorry. Right, so Scott, you should now be a presenter.
Okay, and can you hear me okay, yes. Trevor?
Yep, I can hear you fine, thank you.
Yeah, Trevor, I'd like to thank you for your gracious introduction, and I'd like to thank everybody for attending this morning. Like Trevor said, the topic of today's discussion is performance and tuning for streaming IMS CDC data to Kafka. This is a very, very hot use case these days and has been for the last, 18 months. It's starting to heat up even more, and I think you'll see why as we go through this. So I guess we hold questions till the end, but here we go. So we'll start with a little bit of introduction about me. Trevor said, gave me a nice introduction. My love of what gets me up in the morning is the ability to work with customers on complicated use cases. And like I said, lately it's all been about streaming to Kafka. Kafka's hot. You'll see why as we go through it. And then we'll get into a little bit about what Kafka is, talk about some of the key performance considerations, talk about the initial loading and the actual CDC streaming, a little bit touch on the Kafka producer performance factors, and then discuss common operational issues that we see, and then we'll wrap up with the Q&A. So what is Kafka? Kafka is a ultra-fast distributed stream processing processing platform for big data. Think about it like MQ on steroids. It open source, an extremely large community. So there's a lot of support for this, and most vendors have a flavor. So Cloudera has their flavor. Amazon has their flavor. Of course, Confluent were the ones that brought it to the table. It actually got started at LinkedIn, and they open sourced it, I believe, in 2011, and it's evolving very, very rapidly. It's very scalable. It's fault tolerant. As we go through here, you'll see us talking about topics. Topics are basically queues. Partitions are just that. They're separate log files. So a queue is a log file, not necessarily a page set, but you can equate that with a queue. And so architecturally, you have producers on one side, on the left, pushing messages to a Kafka cluster that can consist of multiple brokers for scaling. And then on the back end, you've got consumer groups, more and more consumers that pull data out and do with it what they need to do. They usually end up in a NoSQL database or some sort of analytics. You could use it for fraud detection and so on. At the bottom is Zookeeper. And Zookeeper, just like the name implies, kind of keeps the zoo in line as far as managing topics and processes and so on. We won't talk too much about that, but just to know this is a basic architecture of Kafka. Now, interest over time, and I find this interesting, and no pun intended. The Hadoop is in the red, and Kafka is in the blue, and this is since January 1st, 2013. You can see that Kafka is on the rise, and Hadoop is going the other direction, and just slightly. But Hadoop is a solid technology. It's a nice file system, but not great for real-time streaming. You're near real-time streaming. Kafka is taken over from that, and that's what it's meant for. So, like I said, very hot these days. Now, this is a slide I have in most of my presentations, and it comes into play, especially in this environment. So I call it the Great Divide. So on the one side, you've got your mainframe folks, legacy, IMS, DB2. That's the group I'm from. I'm more on the left side. And then on the right side, you've got the distributed folks, architects, the Kafka guys, the Hadoop guys, the analytics. And in the middle, there's a huge gap. Now, it's rare that in some of the better, more progressive customers, you'll see a bridge between the two, and there's actually a pretty good bridge. But in most cases, the two groups don't really talk to each other very much as far as other than requirements. They might not necessarily like each other very much, because of frustration. And the discipline is definitely different. So the discipline in the mainframe and the discipline on the other side, they're night and day. You've got this discipline on the mainframe, but not necessarily on the other side. And we've got an example of that here in a few minutes. So within Kafka, they have replication factor, and this is what makes it so highly tolerant. So you've got a producer, CDC stream, if you will. It's going to go to, say, a leader. In this case, the pink is the leaders. You can see these partitions. There's 3 brokers in this setup. When you write to the leader partition, and the leader broker, rather, he goes to, like, for example, partition 0, and then Kafka, under the covers, will replicate those to the other 2 brokers. Okay, and once the committed records, the records are all committed to everything, then they're available to the consumer. This kind of becomes important for performance, and we'll talk about that here in a minute. So, transaction scope. This is a big deal. Because it's different. It's a mix of ACID and base. So IMS being ACID, commits, rollbacks, true transactions. Target Kafka being based today. Really no commits and rollbacks. You have acknowledges, but not necessarily on a transaction boundary. And I say today. That's evolving quickly. They're moving into a transactional based option. We haven't really seen it yet. It's set up for the Java Connect the jury's still out on speed, but Kafka moves so fast that I don't have any doubt that these guys can make it work. But as far as the commit scope, each message is acknowledged. So if you have a transaction with 10 updates, we get acknowledges from every single message going into a topic. Again, it's not necessarily transaction-based, so each topic's independently acknowledged. Now, the other concept is you have delivery options. You have, or acknowledge options actually, at most once, at least once, and exactly once. And at most once means it's the fastest. There's a little typo here. You can lose data. This is kind of fire and forget. What that means is you'll get the message in a topic at most once, but it could be zero. Important data you do not want to use at most once. At least once is durable, but you could have duplicates. Says it's at least one time, but you could have more than one for the same message. And exactly once is something that's come out over the last 2 years. Actually, they had it spec'd out 2 years ago and not even implemented, where messages are logged exactly once with no duplicates. There's a slightly additional overhead on the producer. It's all done within Kafka, but not terrible. So what does this mean to us? Is your commit scope is based on business requirements, and today I'd suggest planning for duplicate messages. Eventually you won't really have to do that, but it can't hurt. And like I said, it's evolving very, very quickly as a transaction-based system. Okay, deployment model. This is a common deployment model from some of the more successful customers that we have. We have several, and they're all of similar architecture. So on the left side, you've got your capture and ingestion. They call it ingestion. It could be apply. We know apply engines. They're called ingestion. Then everything goes into red zone, highly secured red zone. Data goes in as is from the mainframe, so sensitive data exists in this red zone. Nobody can get to it. And then in the middle, you've got transformation, masking, filtering, desensitizing data, and so on. And that ends up in the green zone. So there's two zones if you're dealing with sensitive information. The sanitized data landing is the one that's ready for consumption by downstream people for analytics and so on. If you're looking at an application modernization use case, then there's less of the masking and so on, because you actually do need that data if you're trying to replace applications. Now, an important note is each of these components, transformation, especially the masking of sensitive data, you'll find vendors that have tools to do all this, but we've always been under the thought that you need to do something and do that thing very, very well. And so what we see is you pick a CDC tool, and there's several. Well, actually, in the mainframe, there's maybe 5 or 6 that handle IMS with competence. In the middle, there's all sorts of masking tools, open source, transformation tools, filtering. Filtering is kind of a no-brainer, but it's more on the masking side, desensitizing side. Really, what you want to do is take the best of all and use it as a framework. So where this is your CDC plumbing on the left, in the middle, don't settle for just any vendor's solution. You might want to look at open source and what everybody's doing, the ones with larger communities. So enough about the Kafka details. Let's get into performance. So throughput and latency in replication, and that's not just for Kafka, it depends on the speed of the target. If your target's slow, your throughput's slow, your latency's going to be slow as well. Now, Kafka is a fast target, an extremely fast target. What we see is where you may, say in DB2 or any relational database, look at a single thread at 2,000 a second, maybe 2,500 a second. Kafka can do 50,000 a second and even higher depending on message size, which is the top item that affects performance and throughput, is the message size. Bigger messages take longer. I mean, they just do. How about you scale for that? Affects performance and throughput. The initial load, the volume of data, Streaming is really transaction size and arrival rate. And then Kafka configuration itself. Message size. It really boils down to bytes. You know, people talk about message sizes and everything, but it's a bit obvious. It's small messages perform better than large ones. You hear people saying, well, Kafka can ingest 1 million messages a second. Well, they're probably like 10 bytes each. You know, it all comes down to bytes. We see production in the half gigasecond range in some instances, and in the 250 meg a second range. It depends on the configuration. But we do know this. IMS segments can be large. You know, we're dealing with some segments that are 8,000 bytes, 10,000 bytes. And the updates actually have both the before and after images. You can configure that if you have the right tool to not get both, but most people want both. So what do you do about this? First, use Avro as your target data format. It's a binary format. It's a condensed version of JSON. JSON is like a light XML used for data validation for the most part, can easily be read, monitored, and validated. Avro messages are roughly the size of the source segment, times 2 for updates. So however big the IMS segment is, Avro messages will be similar, but if you're to try to ingest JSON, then you're talking significant additional bytes. Will slow things down. The other thing you can do is reduce the number of fields in the CDC message. Maybe you don't want everything. You want half the fields. What we see is that customers are choosing to select everything and then let the consumers pick and choose what they want. What they don't want to do is go back, and this is where the DBA comes in. It's like, oh, now we want this field. Now we want this field. If you give everybody the fields, all the fields up front, then you don't have to go back and revisit. And then, of course, compression. That goes without saying. It happens in IMS as well. LD4 appears to be the most stable method on that, but compression definitely speeds things up as well. This next slide is a sample IMS CDC record in JSON format. You got some metadata here at the top. What the object is, it's the database segment. The store clock of when the update happened, the timestamp, the sequence number within the transaction, and this is how we do the metadata. It could be done a multitude of different ways depending on the product. You might have the parent key, and then you have an after image and a before image. And in this case, you can see that the amount changed from 2964 to 4087. Fairly straightforward, but easily read and validated. Okay, on to IMS. Let's talk about the initial load. The initial load is one of those things you need to prime the target initially and for recovery. Now with Kafka, you load IMS in search. There's really no traditional utilities like a high-speed unload and reload. Well, there's a high-speed unload on IMS, of course, but not necessarily high-speed reload on Kafka. It's just as fast to write in mass for the most part as it is to do inserts as you go along. You need to be able to scale on both source and target sides. And then really important is you need to be able to run unloads against live databases. That's critical. Nobody takes an outage to take 4 terabyte database offline for backup. So you need to be able to run unloads against live databases. And on the Kafka side, you really want to use what we would recommend as best practice is a separate set of topics for the initial load. That puts the burden of the merge between the initial load and CDC on the back end, but it's clean, and we've seen the successful implementations that this is what they do. So architecturally, you've got IMS, of course, an unloader process and a publish process down to the ingest engines that load into the topics. If you use an Avro, that's where the source schema registry comes in. The framework that we use is to make these look like CDC records, so there's no separate processes. You could actually use an unload image copy, like an online image copy rather, and ingest with that, but the process between that and CDC would be different. And our take is to keep things as simple as you can. So if you want to scale, we start with the target side. Like I mentioned, the target's always the slowest. let's start on the target side. So you want to parallelize the ingest engine. Your engines need to be able to scale, parallelize, like multi-threaded applies off of one subscription from a publisher. And the key is, scale as you can, the publisher latency should be within a tolerable limit. And the tolerable limit could be sub-second. It could be within 2 minutes. It depends on the business requirement. So this is the first place to start, target side. Then you move into source side. So what you do is you'll have multiple subscriptions from the same publisher, usually split by database or partition. And then you maintain the parallel ingest engines on the target side, again, one per subscription. So you have 3 sets of parallel engines. In this particular example, again, the desired behavior is that the publisher latency should be within a tolerable limit based on business requirements. So say you're still slowing down, you're not fast enough. Then you get into source side scaling. And this is something that happens last, usually, where you have multiple unloaders and publishers at the same time. It's used for high data volume, and I mean like terabytes of data where you need to be able to do the initial loads within a day or so. Minimal time for initial loads this way. You can run everything in parallel, and really what you're stressing out is network. And when you get to network, is your limitation, you're pretty much maxed out. Scaling additional will help. But most people run very, very, very fast networks, and we have really seen that being a problem. But we do see, parallel processes all the way down, and you can unload a lot of data in a very short amount of time. Okay, on to the CDC streams. Basically, 2 methods of capture. Well, 3. 2.5. You've got the log-based capture, which a lot of people use. That's where you have your hex 99s. Good and bad. For example, if you have kicks, you got hex 99s. If you got DLI batch, you're stuck with the hex 99s. The downside is it increases logging. And for fast path, that could double the updates for those given segments in a fast path database. So some people stay away from that. The other method is the data capture exit. The data capture exit doesn't use hex 99s. It's ideal for fast path, but if you got kicks or DLI batch, then it's really not an option for you. Of course, you can mix and match. Depending. Not one size does not fit all. You have to look and see what works best for you. We have customers that run both, and then you've got vendor proprietary. We call over the top. I think there's 1 or 2 examples of that. One piece that I've seen that it's log based, but the vendor uses a logger exit, DFS FLGX0, and what that does is captures the hex 99 as a written to the log, the IMS log. Well, that's a choke point. If you see that architecture, I would suggest running very quickly away from that. You will slow down IMS. If something bad happens, you might even take an outage. So if somebody's using that logger exit for anything other than DLI batch, it's a handy piece for DLI batch and run quickly. For the rest of this discussion, we're going to assume log-based, but it could be, the capture exit, looking at the publisher back to transient storage. What we recommend is a similar architecture to the initial loads. Keep things simple. You don't have to change any of your ingest engine configuration. You need to be able to scale on the side, on the source and the target side, just like we did. And then we recommend using a separate set of topics for the CDC streams. Again, scaling, very similar to what we just saw. Start here first on the target side. One publisher, order may matter in this case. If you don't care about transaction order, which most people do, you make sure, if you care about transaction order, that your ingestion engines can handle that, based on keys of the sources. Again, the publisher latency should be within a tolerable limit. You should not have be 1 second back, especially with online. You should be sub-second. So scale on the target side until you get to that. If you cannot get to that, and we have customers that run extremely high volumes, you'll see this mostly not so much on online workload, but batch. When batch fires up, it could be, I don't know, 400 or 500 million updates within a very short period of time. So we want to do the same thing we did for the initial loads, is split the ingestion engines up by database and partition, the same way we did for the initial loads. And again, the desired behavior is the publisher latency should be within a tolerable limit. If that doesn't work and you're still falling behind, then you're looking at additional source side scaling. And we do have customers with setup like this, more than one actually, but they're very high volume customers. We have multiple captures and publishers split by the IMS subsystem or data sharing partner. It's good for segregated workload where you have certain regions that handle batch, certain that handle online. What we would recommend is that you might combine the online SSIDs into one set of captures and then splitting out the batch. But again, it depends on the setup. The customers that we have with this setup do split out their numbers by workload. So it makes it a little bit easier to capture. Now, as far as throughput, acknowledgments in Kafka are the receipt of a message. It happens on every single message. So if you say ACK equals 0, it's a fire and forget. There's no guarantee of delivery, and it's very, very fast but unreliable. We see, say, like wellhead reach with oil well would fall into this for you catching, every 15 seconds. If you miss one, that's okay. ACK equal 1 is acknowledged after the leader broker receives the message. It's very, very durable, but not masterable. And then acknowledge equal all says acknowledge after all replicas receive the message. What this is, it's slower, but it's definitely the most durable. So if you say ACK equal 1, which most people do, if you lock your leader, you may, it's possible, not probable, but very, very slight chance you're going to lose some data. If you wait for everything, then your throughput drops significantly. It might take, 5 milliseconds to replicate to all the different brokers from a single partition, depending on what your replica vector set at. So be aware of this. If you're streaming as fast as you can and the target is just not responding as quickly as you want to look at these kind of configurations, because eventually it'll back up on the IMS side, and that's not what anybody wants. Okay, batch sizes. Topics, like I mentioned, are log files, and what they have is a concept called offset. So if you talk to the Kafka guys walk the bridge across the Great Divide, go talk to the Kafka guys. They'll talk about, this offset. It's really RBA, really is what it is to tie that together. Writes are appended to the end of the log file. Kafka likes batches, so it can write multiple messages without repositioning. Kind of makes sense. If you're at the end, if you have a batch, you can write a whole slew of these records. Small batches are ideal for low latency and, of course, near real time. Small batches are recommended. Large batches, of course, increase latency and throughput because you have to batch these things up. What you don't want is somebody, 10-minute batching and then write. If you're looking for near real time, don't do it. In the case of IMS streaming, batching is really dependent on the transaction. The way we do it is we'll batch per transaction, or batch might have 10, 20,000 updates per commit, maybe more. Those would be larger batches. Online might have 3 or 4 updates. Those are smaller batches, and you can group those together. There's a trade-off. There's really not much you can do. If you're looking for near real time, you have to process that as the data arrives. So partitioning. If you talk to the Kafka guys, you definitely want them to partition, but don't overdo it. It increases throughput parallelism, highly recommended. It does increase the unavailability if a broker abends. So it takes longer to assign a new leader. There are a lot of partitions. Again, we've seen Confluent came out with some stats saying it takes 5 milliseconds per topic partition to assign. So 10,000 partitions would take about 50 seconds to a minute. That might slow things down depending on your arrival rate on the source side. It can increase end-to-end latency. So on the consuming side, which we're really not concerned about at this point, they can only see messages that have been fully replicated to everything. So if it takes 20 milliseconds to replicate 1,000 partitions between brokers, that could back up. You can see that. 20 milliseconds is something we measure with the calendar. If you're running a larger cluster with multiple brokers, this is alleviated somewhat. But the recommendation per Confluent is number of partitions should be 100 times the number of brokers times the replica factor. So is it to replicate to two different brokers or 3 or 4? So you want to make sure that you stick within this. This is kind of a well-respected calculation on the target side, the broker side. So let's get into some operational situations. You'll see this. We've seen it. We see it pretty much every day. We start with the target side. So on the target side, you can take an outage on the cluster itself or Kafka slow. In the middle, rare, very rare, but it happens. Similar to a target outage, but with a much, much shorter duration. You get a network drop. In the case of network drop, make sure the tool you use picks up where it left off with no data loss, minimal duplicates. On the source side, one that's probably the most pain is compressed prilog in the recon. If you're using log-based, if you're using exit, it doesn't matter as much, if at all. And then if the capture publishes are out down or they're slow. So we'll start with the target side. And what we got here is the target's unavailable to receive data. The ingest engines fail. This is no different than if you're going, say, from IMS to IMS, if you're going from IMS to DB2 or Oracle. If the target's down, the engines drop. It's very rare for Kafka to lose a whole cluster, but it can happen. I was talking to a customer yesterday, actually, and they were saying that the Kafka folks took down the cluster for maintenance at, say, 6 o'clock on Friday night. Well, the maintenance window for mainframe is Sunday morning early, and so things started backing up. Here we get into discipline. They might just reboot in the middle of the day. They might start their own maintenance cycle. So you need to really get on the same page, get them on the same page with you. Mainframe side drives the show. But that's really what we see if cluster going down. They just rarely fail completely. But if it does, they start backing up on the source side. So you have two options. Wait until the cluster is available and restart. That's okay if it's a short period of time, depending on your transaction rate. If you got high volume transactions, that short period of time might be an hour. If you got low volume, you might be able to go a day or two, depending. But eventually, you're going to reach a point of no return where you can't catch up. You won't be able to catch up. There's just for extremely high volume. If you're back 2 days, you probably won't be able to catch up. And so we call that the point of no return. When you're into the point of no return, you're probably looking at a reload. It's a very, very bad situation that you want to avoid. So the second option kind of alleviates that a little bit is spin off CDC data to a separate file. And so a utility to do something like that, this ingest engine is not going anywhere to Kafka because he's down. But if you have the right tool, you can actually spin this off to a CD to files on the distributed side. Data does not back up over on the mainframe, and then when the broker comes back up, you can have the ingest engine run against the files until they're fully consumed and they connect back to the original setup. This is a pretty common deployment. Now, if your cluster's slow, this is again where throughput's measured with a calendar. again, data starts to back up on the source side. You kind of see the pattern here. If the target's slow, data's going to back up. So what are the common causes? You got one or more Kafka brokers down. Try to correct and restart. Out of memory issues happen a lot. They'll slow things down. So your round trip might be, not sub-second, but 5 or 6 milliseconds. That's not a good sign. This is one of the key pieces here. Queued max requests, set it to a reasonable value. You think putting it higher is good. It's not. The default is not bad. I think it's 500 max requests queued for input. Memory buffers should fit entirely within RAM. You don't want anything swapping. And then log files, just like any kind of disk I/O that you'd have on the mainframe, need to be the strategy need to be reviewed and set. There are lots of different settings for this. We won't get into that at all because that can take, seriously, days. But the key is to leverage monitoring tools. The Confluent Control Center is an excellent tool for that, and there's others that monitor Kafka for these kind of conditions. So it's just like monitoring DB2 or IMS for performance. The same thing happens on the Kafka side, but this guy needs to be fast. If it's perpetually slow, you may need to back off CDC until they tune it right. We'll see that. You go into production with a high volume application and Kafka's not ready. It won't be for another week because the disk is slow or whatever. They might have to back off until everything's tuned and then restart. Okay, this compressed pry-log in the recon, this happens. The SLID's data set still exists, but the entries disappear from the recon. And so the whole point of this is to, what IMS thinks is the SLIDs are inactive, don't need them anymore. We can reduce the size of the pry-log in the recon. And unfortunately, CDC thinks otherwise. Tools, there could be valid CDC data in those logs. A lot of tools will not handle this. And if your tool can't handle this, and you're looking at unwelcome, and I say unwelcome is with bold, if you will, manual intervention and maybe even a reload, depending. The manual intervention is extensive, and DBA is usually the one that gets to do that, the IMS guys, and they have better things to do than this. So your replication tool really should have a method of getting you out of the situation. So you want to ask your vendor how do you get out of a compressed pry-log situation. To avoid it in the first place, you can increase the DBRC log retention period. Be careful with that if you got a lot of activity with a lot of archives. So if you're archiving every 3 or 4 minutes, 5 minutes, your recons get big, and that's the whole point of log retention. You want smaller recons, but you can increase the log retention period and try to avoid this. But if it happens, you definitely need a way out, or it's not a good situation. If the capture and publisher components go down, no data is flowing at all, but the downstream folks, there's no performance issues there, obviously, no data flowing, but they're getting concerned, and phone calls are being made, and escalation and all that good stuff. Well, if it's because LPAR goes down, the tool should just fail over to another LPAR and resume where you left off. You need to have that high availability built in to your processes. Transient storage is backing up. Allocate more space if possible. If not, you just need to figure out why. Is it because of a slow target? And we go back to that. Why is transient backing up so high without the throughput? It may take a while to catch up, so be patient with that. It might take, for 10 hours worth of work, it might take an hour and a half or so, an hour, hour and a half to catch up. But if you can't restart, of course, this kind of goes without saying, contact the vendor as soon as possible. Step 1, can't get restarted, things are backing up, the business is suffering, and so on, and see what they can do to help you out of that jam. Now, the IMS publisher being slow, Kafka's not doing much. The Kafka guys say, well, there's nothing going on. CPU's not running hot. There's barely any data trickling. The issues on the source side. So we see common causes here, the busy system, processes running at a lower priority. Just increase the dispatching priority if you can. It might just be an overly taxed system, and we see that. with the smaller guys, guys running 50 MSUs during batch, nobody's getting much time there. Abnormally large units of work. And we see this from time to time, not so much in IMS, but it happens. Somebody unleashes the beast that updates 100 million records with a single checkpoint. Purgers tend to do this. And when I say purger, the mass deletes. You may want to exclude those purger jobs from capture at all, because downstream doesn't necessarily want to see a bunch of deletes come through. They'll purge on their own. And the other piece we've seen is in multiple accounts is the TCP/IP window size shrinks. It's a firewall thing. I'm not a network guy, but we've seen it go to a very, very small number. We want to try to avoid that. But if that pipe, was a big huge pipe, now it's a little straw because the window size is too small, there's no throughput, and it looks like everything's slow, but publishers waiting, Kafka's getting nothing, and so it's a little straw in the middle that's probably causing that. At the end of the day, you want to make sure that the CDC tool on the source side provides appropriate monitoring metrics for you to detect this kind of thing. Latency is probably the most important. When was the last commit received from the target side? That's important, and so on. There's several that you want to monitor through automation. Okay, we're coming down to the end here. To summarize, really, keep the ingestion method as simple and consistent as possible. The initial load CDC streams using the same framework is ideal. Less work on your side, on the mainframe side. Understand the business requirements for end-to-end latency, whether you need to scale or not, what's acceptable. If you need true near real-time sub-second, you're going to probably require more scaling than those who don't. And again, it really depends on the transactional level rate. Scale to satisfy the business requirements, but don't overdo it. We've seen some folks plan initially upfront before they even get their Kafka cluster installed for scaling. We're going to need to scale. We're going to need to scale. No, start simple and build up to meet the business requirements. Don't just go all out scaling for day one. You'll find out very quickly, and you can scale as you go. Have a good recovery plan. Really important, like what we mentioned, spinning up the CDC records to disk if the target's down, and then have a fast way to reload source data if you have to. You really want to avoid that. Sometimes you can't. But if you have all this in place, then you don't have to scramble if it's time to do that. And then be patient with the Great Divide. You'll need every bit of that patience, trust me. And we see it. We try to bridge the gap, but there's a significant amount of frustration, mostly with discipline and expectations. So be patient. And then, of course, I always end with selecting the right tools for the job. At this point, Trevor, we're open to any questions?
Okay, if anyone's got any questions, then if they can type them into the Q&A box, we'll get Scott to answer them for us. I'll give people a couple of minutes to type things in.
Yeah, don't everybody jump in at once.
Or if no one seems to have any questions, and you've answered everyone's questions, what I'll do is I'll take back control, and if any questions come up, then I'll stop what I'm saying and get you to answer them. Does that sound like a plan?
That sounds great.
Okay, let's change roles. Presenter. And let me share my PowerPoint. Ooh, okay. Right. Let's see how I can get on with this. before I do move on, I think it's only fair to say thank you very much to Scott for his presentation. Like I say, if questions do come up, I will ask him in a moment. But Scott, because we're a virtual user group, as usual, can you assume that you're now hearing a virtual round of applause for your presentation?
Thanks, Trevor, and thank you, everybody.
Yeah, if you can just hang on for a second, and we'll see if we get any questions. So I haven't got any news for you, but just a reminder that IMS updates quarterly now, so you can always look out for that. In terms of articles, then we've got Get IMS from the Cloud to Your ZOS Environment. That's by Dipti Gandhi, and that's on Z Systems Developer Community, and that was put up on the 4th of April. There's a link to that on our website on the articles page. Can I ask for feedback about this meeting? Again, you can email your comments to me, and the address is on screen, or you can use the Contact Us web page just to let us know what you thought. So, meeting dates. As you can see, our next meeting will be on the 11th of June. We've got James Martin, who's a Senior Solutions Advisor for Rocket Software, and he'll be discussing what's new in IMS Connect Extensions version 3.1. And then after that, we've got 6th of August, Dusty Rivers, Director of Z Systems Software, IMS and Kicks at GT Software, and we haven't got a title for his presentation yet, but usually very enjoyable. So 2 dates for your diary. Okay, yes, can I remind you that you can keep up to date with what's happening in the world of IMS and on the Virtual IMS User Group website by following us on Facebook and Twitter, and you can also join the Virtual IMS group on LinkedIn. The URLs are all on the home page of our website. They're also on screen if you can memorize them now. Yes, everyone likes, so if you're on Facebook, if you can like our page, and if you do anything on social media, the hashtag we'd like you to use is hashtag VirtualIMS. Okay, just before I do that, let me go back and see if we had any questions. Okay, no, there weren't any questions. And Scott, you can relax. So that's all for this meeting of the Virtual IMS User Group. Can I thank you all for attending? I must thank Rocket Software, they're the people who sponsor this user group. And I particularly want to thank Scott Quillisi again for today's presentation. So that's it. Thank you all very much for joining the meeting, and I look forward to seeing you next time on the 11th of June. So thank you all, and goodbye.